Hey guys, I hope you're having a great day. I wanted to go through some of the notes that I gave you with you. And so I'm going to try to keep it brief, even though we're going through a whole chapter at this one point. A lot of the material that'll be on either a quiz or a test will come from this video, from other videos that I upload for you, or as well as just reading through some of the notes. There's there's not as much material as there would be if we were at school. I've tried to condense some of it, and I think you'll like the notes this way. But I'll go through, highlight a few points for you, and then you can watch this over and over again if you need it. But you can also just read for yourself. Some of the information is pretty straightforward and self-explanatory. And so I hope that this will end up helping you as we move forward with this chapter. So this chapter 15, we finished on climate. That was chapter 14. Now we're moving to oceans. And so oceanography itself is going to be the study of Earth's oceans. That's what we're going to be doing. Ways that we do that is through data collection and analysis. A lot of basically what science is taking information that we have learned or collected or seen and then trying to understand what it is we're looking at. And so on the surface or at sea surface level, we can use sonar, which is sound navigation and ranging. What that does is that shoots out sound waves down, and as they reflect and come back, we can use that to put together an image to try to map out the ocean floor. Other ways we do it are floats or buoys that will be just floating along. They collect information on water temperature, salinity, which is how much salt is in the water, as well as other various gas and nutrient concentrations, and wave motion. And then satellites up from above can beam down, use infrared technology like we've talked about before to scan the surface as well as monitor surface temperature, currents, wave conditions, and much more. At the deep sea level, we're going to use remotely operated submersibles, things that can go underwater. Sometimes they'll have people in them, sometimes they won't. That's where that remotely comes from, to explore new areas and hard to get places that we wouldn't otherwise be able to study. And then we can use computers to compile all the data that we get from both places, and then that helps us to figure out, understand what we're looking at, produce models to show other people, to help us figure out what life in the ocean, around the ocean, might look like if there are changes. The distribution of Earth's water. The Earth is known as the blue planet, rightly so, because 71% of our surface is covered by ocean. One of the labs that we would have done is if you would have taken a string and wrapped it around the equator and then taken the amount of inches or centimeters that were touching water and then, divided those by the total, it would have come up with around, I think it was like 71 or 72%. And so I hate that we couldn't have done that, but you're still getting the information. The ocean, so that's of that 71%, oceans contain 97% of the water found on Earth. The other 3% of all water is fresh water, and so that 71 might be a little higher if you include other freshwater sources. If we look at the northern hemisphere, not to go in too far, we can see that the northern hemisphere is covered by slightly more water than land, but there's a lot more land in the northern hemisphere than there is in the southern, which is almost completely covered by water. I'm clicking the wrong button. I'm sorry. Zoom out. All right. Here we can look at this chart. It just reiterates what I said earlier, that 97% of the water on Earth is going to be salt water in oceans, and only 3%, very small percent, of that is going to be fresh water. There's only one ocean. I know that people have said there's different oceans, and then there's only one ocean, but those oceans are going to be divided into geographic regions by name. And those the different regions of the ocean are the Pacific, the Atlantic Ocean, the Indian Ocean, the Arctic Ocean, and the Southern. You can see the Southern there, the Arctic there, and so your, I'm looking at correctly, Pacific Ocean would be over here, your Atlantic Ocean would be over here, and I don't see your Indian Ocean would be in this area if you're looking at a globe. Oceans provide moisture and heat to the atmosphere. They help influence a lot of weather and large-scale circulation patterns as that move wind and currents around the world. And they also are a vast reservoir, which means that they contain a lot of Earth's carbon dioxide. I know we talked about a lot of it being in the atmosphere, but the ocean itself is going to hold a large amount of it as well. If we look at the chemical properties for this, we can see that it's going to contain a lot of dissolved oxygen and carbon dioxide, as well as nitrates and phosphates. A lot of this will contribute to the salinity, or the amount of dissolved salt. Salt's going to be expressed as parts per thousand, and the way you get that number is you take the amount of salt, and for how much ever water there is, and that's where that comes up with that number. The average salinity of the ocean, meaning if you took the median of the whole planet, it would be about 35 parts per thousand, but that varies with location because some have more and then some have less. 35 is just the average. Your lowest salinity will be found near estuaries, and that's where salt water and freshwater meet. Think of where rivers dump into the ocean, like where the Mississippi River dumps off down by New Orleans. That would be an estuary. Geologic evidence, I found this neat. Geologic evidence shows that salinity has not changed over time, so that our oceans are actually going to be near that same 35 ppt now as they were however long the Earth has been around. And so that is cool to see that with the way science is always changing and talking about how things are changing and how the world is shifting and climate change and this and that our oceans have remained relatively the same throughout history. The sources of salinity and geologic evidence come from volcanoes and weathering of rocks and surfaces. Volcanoes supply sulfur dioxide and chlorine, and then the weathering of rocks and surfaces supplies sodium and calcium, iron and magnesium. All of these ions can then be combined to form salts of various kinds. Because of its salinity, seawater or ocean water is more dense than fresh water. You can float in it better. In cold water, so if you are in the ocean and you are further north or south near the Arctic or Southern Ocean, the colder the water, the more dense it is. And so density will have an effect on moving currents. So that'll be important to remember in just a second. The salinity is going to lower the freezing point, and so ocean water will begin to freeze at around -2 degrees Celsius, whereas fresh water would be that 0 degrees Celsius. And you can see in Fahrenheit that would equate to 28 degrees Fahrenheit and 32. Light doesn't make it through much. It makes it about 100 meters down, where most light can penetrate to. After that, because light is absorbed by the ocean, a lot of what's reflected would stay in that bluish indigo spectrum, and so we don't see a whole lot of light further down. So most of photosynthesis is going to happen at this point. Once we start moving further down, we get into that aphotic zone where no light will be less light, I should say. That'll start being chemosynthesis, where processes happen in our ocean. And so we don't use sunlight, they use chemicals to produce energy. Other things to look at is a temperature profiles, where we layer levels of water on top of each other and compare them. And we can see how, if we look at the different oceans areas, so you have a tropical region, the temperate, and the polar, those three zones on Earth, the surface temperature of those waters, and then how they change with depth. We can use temperature profiles to look at that. So you have the surface layer temperature and then the thermocline, which is a transitional layer between the surface and the bottom. And that helps to transition the temperature a little bit. But the further down we go in depth, you can see that regardless of location, temperature is going to drop to about a relative number the further down we go. That's because cold water is more dense and it's going to sink to lower depths, whereas that warm water is going to rise up to the top. And that shifting of cold and hot is going to create currents down below that help move. And when you can see some of the currents you see on top. A lot of what you see on top will be generated by wind, but the stirring of water down below helps to generate some of that, move some of the heat we see in oceans as well. Looking at waves and how those play effect into the ocean. Waves, scientifically speaking, are going to be rhythmic movements that carries energy through space and matter. Our space and matter in this case would be the ocean, and so as energy moves through ocean, we don't oftentimes see the trough or the low points. We'll oftentimes see the top side of the wave, but as the wave moves, we can see that energy moving through on top of the ocean. So the way that waves are generated is by wind blowing over the surface. Wave height, or how tall the wave gets, depends on three things. Fetch, which is the expanse of water that the wind blows across. So how big is the body of water? The wind duration, which is how long is the wind going to last for? And wind speed, how fast is the wind blowing? The longer or faster the winds can blow, the larger the wave height. So you'll have bigger waves. So if you have a large body of water, then you need wind to blow for a long period of time. If wind's not going to blow you can have slow winds over a long period of time creating large waves, or you can have fast winds over a short period of time creating large waves that crash almost immediately. Breaking waves are going to happen as the wavelength decreases, so the amount of space between these will get shorter and the wave height will increase. And so they're going to be, there's going to be a smaller distance between each wave, and each wave will gradually get taller and taller until it can't support itself, causing a collapse. And we see that happening as waves crash onto the shore, if you ever go to the beach or watch a beach movie. Other things about the ocean, tides are going to be periodic rise and fall of sea level, happens daily. Tidal experience depends on the landscape of where you're at, the topography, and the latitude, your position on Earth will also affect the kinds of tides that you see. Other factors from space would be the sun and moon. The moon and the Earth moving in a similar direction around a similar gravitational pull is going to cause unbalanced gravitational forces, or because the Earth is bigger than the moon, and as they're moving, there's going to be unbalanced gravitational forces between the Earth and moon, which is going to cause tidal bulges, which you can see here, which kind of pulls on Earth's oceans, trying to tug away at the water that's going to make up our surface. And the sun will also influence the tide, as it has a strong gravitational pull. But because the sun is much further away than the Earth and moon are in relation, it's not going to be as strong as the influence of the moon. There's two kinds of tides. There's spring tides and neap tides. They occur with different phases of the moon. So during full moons and new moons, you'll have spring tides. And so during this time, the sun will enhance lunar tides, causing high tides to be higher than normal and low tides to be lower than normal. And so your high tides will be higher, low tides will be lower. And then during the neap tides, when we're in the first quarter and third quarter moons, the sun is not going to enhance but diminish lunar tides, causing these high tides to be lower than normal. So high becomes lower, and then low becomes high. And so it's the backward effect of what happens with the spring tide. And then tides, once again, like I said, happen daily. You'll usually have a high tide in the morning, or like early morning, usually before the sun comes up. And then you'll have a low tide sometime during the middle of the day. Less likely to have a high tide pulling on the moon during the day, because of the moon, you don't really see it. It's on the other side of the planet. Still has an effect, but you're more likely to see higher tides at night or in the evening. Currents, the way that the water moves. So at the surface, the water movement's going to be generated by wind as wind blows over the water. but deep currents or the movement of water several hundred to 1,000 meters below sea level or surface level are going to come from differences in the water density. They follow at the surface. We're going to follow global wind systems. So if I zoom in on this gyre here, you can see the way that the wind blows across, west to or east to west in the tropic, and then as that current hits some kind of object or landmass, it'll then shift north and south, and then in whatever tropic, temperate or polar zone it's in, it will then move with the temperate district from west to east, and then as it moves back up north some more into the polar area, it'll get shifted back east to west. And so those land masses affect it, and so do the global wind systems. Upwelling will happen when water begins to move towards the shore. And so as wind begins to move north, winds from the north begin to move the surface water here. Water is going to move towards the shore. The Coriolis effect will cause it to spin on top, looking like the water is going to go back out. But underneath, as this water moves either up or moves out, cold water from underneath is going to come up from beneath it and then replace that water. And so that's called upwelling, was when the water from below replaces the water that is on the surface. Deep currents will be determined by the differences in salinity and temperature that generate the currents underneath. And so this isn't driven by wind, but the differences in how much salt there is and temperature at the various levels or layers. So the deeper you go, the cooler the water, obviously towards the surface is going to be warmer. The difference between those, and as cold water sinks and warm water rises, the change there is going to drive movement. Much like with when we studied the atmosphere, when you had warm air trying to rise into the atmosphere and cold clouds sinking for conditions to be stable, that cloud had to rise and then sink back down once it cooled off to become stable, because if it kept rising, it'd become unstable, and that generates energy. And so that's what's happening underneath, just like it was in the atmosphere. The water cycle, if you aren't familiar with it, remember that water will collect in areas, it'll evaporate up, condensate. As it condensates, it makes a cloud. Once those clouds become heavy enough, it precipitates. That water then runs off or lands back in the ocean, and the process starts over again. All of the water is being recycled. As water is recycled, it also helps leave salt deposits and carbon deposits and other materials in the ocean, because it's just pulling the water out. It's not pulling everything else out with it. And so that's one of the ways that things get deposited into the ocean. Looking at the carbon cycle, like I said, the ocean is one of the largest reservoirs of carbon. And so how it works is that there are living things. As living things die and decay into the ground, carbon gets added layer by layer. There's also natural resources of carbon that are deep down that we take out and use for fossil fuels and things like that. Those get released into the atmosphere. So there is carbon dioxide being released, or carbon just in general released into the atmosphere. Biomass, whether on land or in the water, are going to try to recycle that down through photosynthesis and replace it with oxygen. But other organisms might also use it for respiration and decomposition, which puts it either back in the ground or back in the air. And so a lot of times, if it's not making its way into the ground, it's being deposited in the ocean. And so a lot of the photosynthesis right here, actually, that I talked about earlier, most of the Earth's photosynthesis happens in the ocean. I think I was reading about it being 70 to 80% of photosynthesis happens through plants that are found near the surface across the ocean, or organisms across the ocean. And so a lot of our photosynthesis happens this way. And then as the carbon gets put out in respiration for those things, that's when its deposits make its way into the ocean. Little fun fact for us is that 95% of the ocean is unexplored. And that came from NOAA, also the National Oceanic and Atmosphere Administration. That's what it is. And so you've got National Oceanic Atmosphere Administration. All right. I remember I said out. So they're like the leading government body on the study of oceans around the world. And they've released that 95% of the ocean is unexplored. So everything we know about oceans only makes up about 5% of the actual what we've explored. So that's crazy to think about. That everything you know about the ocean has only been studied from 5% of it. And it's actually been said that we know more about outer space than we do the ocean. And I was reading where that, and you can even sit down here, that Earth's largest mountain range is in the deep ocean, and it's less explored than the planet Mars. We've spent more time studying the planet Mars than we have some of our own ocean mountain ranges, which is crazy. And then to think that there are more species of variety in the ocean than on land. So there's more organisms in the ocean or in water than there are land animals. And then you think about that over 90% of all living organisms are living in the ocean. And so we only really see about 10% of organisms on land. So there's probably organisms, and if we've only studied 5%, that we don't even know about. And so that's crazy to think about, because there's just how vast and how big our world and ocean is. Which leaves me with a parting thought for you. I was just thinking about this. And then also how to encourage you too. It says, for the Lord will be filled with the knowledge of the glory of for the earth will be filled with the restart. For the earth will be filled with the knowledge of the glory of the Lord as the water covers the sea. And that's Habakkuk 2:14. And just to think about how deep and unexplored the ocean is, and how the earth is filled with it, and how there's just so much that we can't comprehend, especially in a time right now. But that the glory of the Lord is just more than we can understand. So that is just something to think about and to ponder on. Like I said earlier, most of what we need to know for homework or the quizzes and your test, other note-taking quizzes or whatever I give you, can be found by watching this video, reading through our notes, and any other videos that I share with you. So I hope that you have a great day, and I hope that this was helpful to you.